Okay, so first, let me talk about the test, and there's a lab test on Friday. Let me talk about both of those. Um, so exam 2 is tomorrow, Wednesday, and the topics are everything up through 2D particle kinematics. Um, okay, and then the lab exam 1, is Friday. Um, and the topics for that are the kind of questions that we did in all the labs so far. Uh, so to start, I'd be happy to answer any questions you have on any of that stuff. Um, Anybody have any homework questions or lab questions? Yep. Yeah. Why don't I think maybe I shouldn't just go through them start to finish because it would take the whole class, but I'd be happy to answer specific questions about any of them. Do you have it with you? I don't think I have it in here. Um, so this is sort of a funny one. The lab. I mean, not the question. I don't consider this like one of the things. Like this stuff isn't going to be on the lab exam on Friday. This was more designed to help you kind of put concepts together for the test that's on tomorrow on Wednesday. Um, and the questions on the test are going to be more like the assigned problems and less like this. It was just sort of to try to make you put these ideas together. But I think these are useful questions. Um, so extra problems number 2. Um, so the idea is in order to get astronauts ready for apparent weightlessness, you send this plane sort of looks more like a dolphin, but it would work with a dolphin actually too. It's just harder to make it accelerate the way you need it to. Um, so you send this plane in a motion that simulates free fall. Okay, so you started out sort of aiming up, and you make it go through the arc that corresponds to an acceleration downward of 9.81 meters per second squared. And the effect of that, even though you're still, experiencing full Earth's gravity, the effect of that motion is that the people inside feel weightlessness. And by the way, I think it's sort of commonly believed that astronauts experience weightlessness because they're so far away from the Earth that, um, that the Earth's gravity doesn't affect them. But that's not really why astronauts in orbit feel weightlessness. Um, like on space stations or whatever, they're experiencing this feeling of weightlessness because of this exact thing. The vehicle that they're in or the space station that they're in is orbiting the Earth, which is actually just a type of free fall. That's what makes things orbit. It's constantly in free fall and sort of falling its way around the Earth. And because that thing's in free fall and they're in free fall, they have this feeling of being weightless, even though both are under the influence of gravity. Um, and so, what does it say? It says that to start, the height is 2,000 meters. And at the end, we're going to finish doing the calculation when it's back to 2,000 meters. The angle at the start of the motion is 50 degrees. And the velocity at the start of the motion, or the speed, is 200 meters per second. And this is something interesting about it, actually. So this airplane needs to go through a motion simulating free fall. So why does the airplane need to do anything? Um, you know, simulating free fall is just being in free fall. Why don't they just turn off the engines? Well, I suppose probably the biggest reason is that airplanes don't keep going forward if you turn off the engine. But another reason is that it's going really fast. And when something's going really fast, there's a lot of air resistance. And so there would be a large amount of air resistance slowing this thing down that would keep it from really traveling in a free fall path. So it has to keep, using its jets to maintain this motion that's simulating free fall. And we want to calculate a few things. First, calculate the position vector as a function of time. Sketch the path of the plane. Calculate the velocity vector at a few different points, and those points are at the start, at the highest point, and at the end. And at those points, we want to calculate the velocity vector. So I'll call that point A, B, and C. I guess that's actually part D. And then it asks us to do some of the kind of stuff that we do in, excuse me, in labs, where we sketch the velocity direction, sketch the parallel part of the acceleration, perpendicular part, compare those. And then the last one, let's just skip down to H. That is if the passenger starts at rest inside the plane, in other words, starts with the initial velocity that the plane has, what is the acceleration of the passenger relative to the plane? And we're going to see that the acceleration of the passenger relative to the plane is 0, and that's where that apparent weightlessness comes from. This person's floating around inside this plane, even though the person's really in free fall, accelerating toward the center of the Earth at 9.81 meters per second squared. Okay, so for part A, we know that the position as a function of time as a vector is equal to the initial position vector plus the initial velocity vector times t plus 1/2 times the acceleration vector times t squared. And since we're looking for this as a function of time, we're not going to choose a specific instant corresponding to t. We're just going to leave that as a variable. If I choose time equals 0 to be at that height 2,000 meters. And the coordinate system to have the x-axis horizontal and the y-axis up, and to be on the ground immediately beneath the plane, time equals 0. Now we can start to fill in these values. T, so, usually I set this up and we figure out which ones we know. T in this case is going to just remain a variable. And that's because we're trying to find position as a function of time. Acceleration is 0, negative 9.81. So even though it's the jets making the plane act like it's in free fall, we can treat this as a free fall problem because it's exactly trying to simulate that acceleration. The initial position is 0, 2,000. We're trying to find the position as a function of time, and the initial velocity is 200 times cosine and sine of 50. That is, I think it was like 128, 153. And we don't know V. But this gives us everything we need to use the equation that I have listed here. So the position as a function of time is equal to 0, 2,000 plus 128, 153 times t plus 1/2 times 0, negative 9.81 t squared. And you can write it as a vector equation like that, or write it as two separate equations. You can also think of this as px as a function of time is equal to 128t. Py as a function of time is equal to 2,000 plus 153t minus 4.905 t squared. Those mean the same thing. Or you could write it as position as a function of time is equal to 128t in the x direction plus the quantity 2,000 plus 153t minus 4.905 t squared in the y direction. And we can also come up with the velocity vector as a function of time. So the velocity, I think this is part D, the velocity is equal to the initial velocity plus AT. And so the velocity as a function of time is equal to 128, 153 plus 0, negative 9.81 times t. And you can write that as 128 in the x direction, 153 minus 9.81 t in the y direction, or rewrite it in ij form. what you see there is what you see in every free fall problem where you have the y-axis pointing up. The x component of the velocity doesn't change, and it doesn't change because there's no x component of the acceleration. So if an acceleration component is 0, then that velocity component has to stay the same, is constant. Okay, so now you can figure out the time, the value of t. Well, the value of t here is 0. You can figure out the value of t there, the value of t there, and plug it into those functions if you want to find the position or the velocity. Let's think about the relationship between the way we treat this in labs and the way treating it mathematically. I mean, mathematically, we know that since it's in free fall, the acceleration of all three of these points is straight down. Okay. And so when we think about velocity direction, a parallel, a perpendicular, total acceleration, the way we do in lab, a downward vector has to fall in the range of accelerations we choose. Okay. If it doesn't, something went wrong. So the velocity vector at this point A is as shown. It's on the way up, and anything in free fall that's on the way up is slowing down. So a parallel is like that. The path, well, I've drawn it kind of sloppy, but the path is curving this way, right? And so
that means the perpendicular is going to go that way. It's going to go in another.
That's right. That's right. So a perpendicular has to go in towards the center of the curve. And so the total acceleration is in between. And a downward acceleration vector falls in that range, so those agree. At B, we have a velocity vector like this. Since it's not gaining or losing height, it's not changing speed at that instant, only at that instant. And so there's no parallel part. Perpendicular part is like this. So that's also the total acceleration. And that agrees with what we know about the acceleration in free fall. And then down at the point C, the velocity vector is like that. It's speeding up because it's on its way down, so that's the direction of a parallel. It's turning this way, so that's a perpendicular. So the total acceleration has to fall in that range. And again, free fall acceleration is straight down and falls in that range. So in that sense, all of these two different ways of thinking about the direction of acceleration agree with each other. Like there's no contradiction, and that's good. You know, something I hear a lot, you know, from time to time, students will come up to me with some work that they did and say, like, does it work like this, you know? And I'll say, no, you know, you actually do this and this and this, and they'll say like, oh, I was overthinking it, you know? And I mean, I guess I sort of understand what people mean when they say they're overthinking something. What they mean is that their first instinct was the right one, you know? But I don't think that's a good way to think about physics problems because really there are so many hints about whether you're going in the right way or not. And when you really understand this stuff, what you're doing is you're combining all of you're thinking about it in multiple ways and they're all agreeing with each other. You know what I mean? Like in this case, like, so like if you did this the wrong way, you know, and the first way you thought about it turns out would have been right. It's sort of natural to think like I should have just gone with my first instinct and not second guess myself. But really what's better is to be able to think like, okay, well, I can approach it this way, and I know that the acceleration has to be like that. it agrees with what I know about the numeric acceleration. You know what I mean? And so really you want to be able to think, you want to overthink it to death and have every one of those ways of thinking about it tell the same story. You know what I mean? Okay, and now let's go to the relative motion problem. So we have three things in this problem. We have, I'll call it the astronaut, the plane, and the ground. And the key thing in free fall problems, and this is the thought process for the problems of dropping an object inside an elevator, or a car, or whatever. It's always the same thought process. In free fall, the acceleration is 9.81 meters per second squared down relative to the ground. And actually, it turns out that it doesn't have to be the ground. It can be that can be relative to anything that's not accelerating. But the idea is, so if you're in an elevator and at an instant that it's accelerating, you drop an object, the acceleration of the object relative to the elevator is not going to be down at 9.81 because the elevator is accelerating. Okay, this only works for a reference that's not accelerating. Usually in these problems, that's the ground. So what you know is that the acceleration of the astronaut relative to the ground is 0, negative 9.81. And since the plane is simulating free fall, you know its acceleration relative to the ground is 0, negative 9.81. So there's two ways to set this up. One is just set it up so that the thing by itself on the left side of the equation is the thing you're trying to find. So let's say in this problem, we're trying to figure out the acceleration of the astronaut relative to the plane. Okay. And now just set up a summation equation where the subscripts satisfy that fraction multiplication requirement, you know. So that says this is equal to the acceleration of A relative to the ground plus the acceleration of the ground relative to the plane. And since A over P is equal to A over G times G over P, you know that this is correct. The only thing about this is like the acceleration of the ground relative to the plane is kind of a weird thing. It's a little bit of an unintuitive measurement, but now just think of this as, you know, remember that if you switch the subscripts, that's the same thing as switching the signs. So this is equal to the negative acceleration of the plane relative to the ground. And now that makes sense. And so acceleration of A relative to P is equal to acceleration of the astronaut relative to the ground is 0, negative 9.81. And then plus negative acceleration of the plane relative to the ground, which is 0, negative 9.81. multiply that negative sign through, and you get 0, negative 9.81 plus 0, positive 9.81, and that gives you 0, 0. And so the acceleration of the astronaut relative to the plane is 0, 0, and that's why there's apparent weightlessness. Okay. If you know those rides at Valley Fair and stuff that where they lift you way up and then drop you, pretty scary. You're way up high in a chair and they drop you. Okay, if they made that ride enclosed, so you weren't subject to the atmosphere, still air, and you were in a closed little cubicle and you couldn't see the surroundings, they'd lift you up there and drop you, and you wouldn't know you were falling. You'd just think you were weightless. There'd be no contact force between you and the seat, and you'd be like, whoa, I'm weightless. But instead, you feel like you're falling really fast just because the air's rushing by your face and you see yourself going towards the ground and stuff. Any other questions right now? Yes. Yes, I'll give you all the equations. Any other questions about the test? Okay. Yes.
For
Mhm.
example, like if you're given with the diagram, like you're trying to give it a diagram, like graph, like for example, give a function of it, and we try to like, do we have to like know what do we have to like draw like the perpendicular? Do we have to draw the acceleration parallel to the perpendicular?
I think there are a couple of questions like that in the homework. So anything that is in the homework, you should be ready to see problems like that. Okay. I'm going to start the next topic, which is circular motion, and this stuff is not relevant for the test.
I thought we were doing particle kinematics, like the topic.
Well, on the test, it's up through particle kinematics. Circular motion, I'm going to call that its own topic, but really, this is another branch of particle kinematics. This is not going to be on the test. We're going to break up circular motion into two different categories. The first one is called uniform circular motion. And uniform circular motion is when the speed is constant. And non-uniform circular motion and that's when the speed changes. Okay, and here's a trick question. Which one of those two produces acceleration? Or which of those two corresponds to acceleration? Both. So remember that acceleration is present anytime the velocity is changing. And velocity has two things connected to it: speed and direction. Okay. And so if the speed's changing, there's acceleration associated with that. If the direction's changing, there's acceleration associated with that. And circular motion, whether it stays constant speed or not, the direction's constantly changing. So the way to think about the directions is so thinking about acceleration directions is what we do in lab. So what we do for 2D accelerations in lab. Except in circular motion, we'll call a parallel the tangential acceleration, and I'll write that A tan. And we'll call the perpendicular part of the acceleration the centripetal acceleration. And I'll write that as A sen. And so the steps for figuring out the directions of these are: first, sketch the circular path. Second, draw the velocity vector tangent to the path. Third, if the object is speeding up, then the tangential acceleration is in the same direction as the velocity vector. And if the object is slowing down, the tangential acceleration is opposite the velocity vector. Notice these are exactly the same steps as for general two-dimensional acceleration. It's just we have new names for these, and we'll also be able to calculate the magnitudes of these parts of the acceleration.
Well, if you go back to your saying now, we'll call. If you go back to we're saying, I think about the acceleration.
Yes. So the parallel part of the acceleration is called the tangential if you're doing circular motion, and the perpendicular part is called the centripetal acceleration. Calling a parallel tangential is, that makes sense because the part of the acceleration that's parallel to the velocity always has to be tangent to the path. And centripetal acceleration means toward the center of the circle. And if you're in circular motion, that perpendicular part of the acceleration always points toward the center. Okay, So fourth, the centripetal acceleration points toward the center of the circular motion. And then last, the total acceleration vector is equal to the tangential acceleration plus the centripetal acceleration. Okay, so if you're in uniform circular motion, then there's no change in speed. Speed's constant. One of these two acceleration terms goes away. Which one is zero? The tangential acceleration is zero. And so in the case of uniform circular motion, all acceleration just points toward the center of the circle. Okay? If you have non-uniform circular motion, then in general, that's not true. Okay. Okay, let's do an example. So let's say an object's moving around a circular path like this. Let's say it's going counterclockwise. And let's say that this is the point we want to think about. So we'll call this the point A. And let's put another one over here. We'll call this B. Okay, so at the point A, the object is speeding up. What are the directions of the tangential acceleration and the centripetal acceleration? And then for B, at that point B, the object has constant speed. What are the directions of the tangential and centripetal acceleration? Okay, so I'm going to do it up on this figure. So at the point A, the velocity vector is tangent to the circle in the direction of motion, like that. It says that it's speeding up, so the tangential acceleration is in the same direction as the velocity. Centripetal acceleration is towards the center of the circle. And if we didn't know anything about the magnitudes of those two vectors, we know just from the way we think about this in lab that the total acceleration is somewhere in between those two directions. Okay. If we do know the magnitudes of those two vectors, then we can figure out components for this, components for that, and just add them together to get a numeric vector representing the total acceleration. Okay, at the point B, the direction of the velocity is tangent to the circle. So this time it's sort of at an angle like this. Is it speeding up or slowing down? Constant speed, so there's no tangential acceleration. All there is centripetal acceleration, and it points toward the center of the circle. And so in this case, we know that that's the direction of the total acceleration too, because tangential is 0. Any questions about that? Yes. Yeah, well, all it needs to be is constant speed at this exact instant. You know, in the next instant, it could start speeding up or slowing down or whatever. But right at this instant, it's part of a uniform circular motion, and so that's all all of these kind of analyses are just totally related to that one instant. We don't know what's happening in the past or the future. Okay. So if now we knew the magnitudes of A tangential and A centripetal, we could add them together to get the vector components of A. Okay, well, that would be great. Wouldn't that be great? We are going to have formulas for those. So now I just have to define a couple more variables, and we're going to get formulas that let us calculate the magnitudes of the tangential and centripetal. And that's the last step we need to come up with a numerical acceleration. We will know them. That's you. Okay. So in order to give you those formulas, I have to define a couple of new quantities. So what we're doing is to calculate the magnitudes of the tangential acceleration and the centripetal acceleration, I need to introduce angular quantities, angular representation of motion. And I'm going to list out sort of all of these angular quantities are going to be sort of have an analogous translational kinematic quantity. So I want to write this out in sort of like a table that relates the translational quantity to the corresponding angular quantity. So on the left are going to be the translational quantities. On the right are going to be the angular quantities. So first, the P, okay, has an analogous angular quantity called the angular position. And we'll represent that with theta. That's just what angle the thing is at compared to some reference angle. And I'll go through the definitions after this. Um, the angular position is going to have units of radians. Second is the velocity vector v. And the corresponding angular quantity is the angular velocity. And we're going to denote that with a lowercase omega. It's like a roundy W. And that's going to have units of radians over time. Third is acceleration. So the acceleration vector A is analogous to the angular acceleration. And we're going to denote that with the Greek letter alpha, goldfish. And the units for angular acceleration are radians over time squared. Now, those are the big angular quantities, but there are also some analogous relationships. So I want to point this out. What's the relationship between the position vector and the velocity vector? Yep, so velocity as a function of time is equal to the position vector as a function of time derivative. And the same relationship holds between angular velocity and angular position. Omega as a function of time is the time derivative of the angular position as a function of time. And acceleration and velocity have that same relationship. So acceleration as a function of time is the time derivative of the velocity as a function of time. And the angular acceleration as a function of time is the time derivative of the angular velocity as a function of time. Okay. So recognize that you can sort of store a lot of these relationships in your head in the same spot, save storage space. And so I guess, so tomorrow's the test. And then on Thursday, I'll finish talking about these. I'll define these angular quantities, and then I'll talk about how to use these angular quantities to calculate the magnitudes of the tangential and centripetal acceleration. Yep. Oh, yeah, I'm glad you mentioned that. Okay.